In part A of this circuit question, we are asked to calculate the equivalent resistance of the 10 ohm and 5 ohm resistors that are connected in parallel. So we can see in the diagram that we are searching for the equivalent resistance of these two resistors. Fortunately, the question tells us that they are in parallel. So in order to get the equivalent resistance, we can use the following equation. So R subscript EQ is what we're looking for in this question, and because we only have two resistors, we'll be using R1 and R2. We wouldn't need the 1 over R3 term in this equation. So we can see that R1 we can choose to call as 10 ohms, and then R2 we can choose to call that the 5 ohm resistor. So we're simply going to plug these in. We'll have 1 over the equivalent resistance is equal to 1 over 10 ohms plus 1 over 5 ohms. Perhaps you can pick up your calculator and type those in together. When you add them, you should get 3/10. And technically the ohms would still be on the denominator. If you prefer, you can actually just leave it in decimal form, which would be 0.3. That's perfectly fine. I like the fraction form because what it allows me to do is a little fraction trick here where we invert the left side of the equation and also invert the right side. So when you invert the left side, you'll get R subscript EQ over 1. We don't really need to put over 1 equals 10 over 3. And now the ohms is in the numerator. Now 10 divided by 3 is 3.33. And that's in ohms. So this would be the correct answer to part A. So essentially what we've done is we've taken these two resistors and we've combined them into a single equivalent resistance. So what that means is we can alter our diagram. We can come in here and erase the original parallel combination, and we can replace it with an equivalent resistance whose value we just determined here. So this is going to be 3.33 ohms. And that's useful because in part B of the question, we are asked to calculate the combined resistance of the 10 ohm, 5 ohm, and 4 ohm resistors. So let's take a look at that. So the question's asking us to find the equivalent resistance of all three of these resistors here. However, we can combine, as just noted, we can combine the 10 and 5 ohm resistors into, this equivalent resistance over here, labeled 3.33. So by doing that, we now see that the resistors that are marked 3.33 and 4 ohms apiece are in series with one another. And that's going to allow us to calculate the equivalent resistance, which is what we want in part B. So for series, the equivalent resistance is a little easier. It would just be R1 plus R2. So calling this resistance R1 and this one R2, all we have to do is simply add them together to get the equivalent resistance. So we have 3.33 ohms plus the 4 ohms, and of course that's going to give us 7.33 ohms. So this would be the correct answer to part B. That's the combined resistance, remember, of all three of those resistors. So now it will be useful to make another redraw. We just combined these two in series, and so what we'll do is we'll make a new diagram, and since we've combined them, we can erase the two and insert an equivalent resistance. So this resistance right here would be the 7.33 ohms that we found above. In part C of the question, we are asked to determine the, the equivalent resistance of the combined resistance found in part B and the parallel 3 ohm resistor. A mouthful indeed. However, what they're asking us essentially is to combine these two resistances together. So those are in parallel. So we go back to the equation for parallel resistors. 1 over Req is equal to 1 over R1 plus 1 over R2. So calling this resistance R1 and the other one R2 will allow us to combine them into a single resistance. So we'll have 1 over Req equals 1 over, go back up, R1 is 7.33 and R2 is 3. So 7.33 ohms plus 1 over 3 ohms. Definitely pick up your calculator here and type this in. And on the right-hand side, you're going to get 0.47 roughly. So it's 1 over REQ equals 0.47. I'm going to do the trick again, so I'm going to put this over 1, and then what I'll do is I'll invert both sides of the equation. So on the left-hand side, you'll just get REQ over 1, which is just REQ. On the other side, you're going to end up with about 2.13. And this is a resistance, so this would be in ohms. So this would be the correct answer to part C of the question. And once again, another redrawing will be warranted here. So we just took these two resistors in parallel and combined them into a single equivalent resistance. So let's erase all of this parallel circuitry here and replace it with an equivalent resistance whose resistance we just found in the previous part to the question. So now we have a new resistance right here, and that has a value of 2.13 ohms. Notice we're whittling the circuit down, and eventually we're going to get a single resistor. We can go back up to part D of this question, and it asks us to, let's clean it up a little, it says to combine the equivalent resistance found in part C with the 2 ohm resistor. So indeed, we will take these two resistors and combine them. Now those two are in series. So again, the equivalent resistance in series will just be R1 plus R2. We're probably getting the hang of it here. So R1 we can say is the 2 ohm resistance plus R2, which is the 2.13 ohm resistance. We add them together and we get 4.13 ohms. So this would be the correct answer to part D. Okay, so let's combine these two resistances into a single equivalent resistor. And the resistance of that equivalent resistor we just obtained, that's 4.13 ohms. Let's head back up and see what's going on in part E of the question. Part E asks us to calculate the total current in the circuit. Total current in the circuit. Now we know from Ohm's law that the potential difference supplied by the battery equals the current multiplied by the resistance. Nice and easy. So to calculate the total current, what we'll do is go ahead and divide both sides of the equation by the resistance. So it cancels out on the right-hand side. We can see, if we come over here, that the total current is equal to the potential difference divided by the resistance. We have the resistance and we have the potential difference, so let's plug them in and see what we get for the total current. So we have the 8 volts divided by the 4.13 ohms. And so when we work this out, we should get a total current of 1.94 amps. So this would be the correct answer to part E of the question. We'll head back up and see what they want us to do in part F. What is the voltage drop across the 2 ohm resistor? So perhaps the best way to understand that question is to realize that the total current will be exiting the battery and traversing this circuit. Now we typically draw the current exiting the positive plate of the battery. So we have a total current of 1.94 amps coursing through this circuit. And then it's going to encounter this resistor right here, the 2 ohm resistor. Now again, the current that's flowing through that resistor is the total current. It's 1.94 amps, and we can see that the resistance is 2 ohms. So if we want to calculate the potential drop, then we simply use Ohm's law. Delta V equals the current times the resistance. So we just take the current that's flowing through that resistor and multiply it by the 2 ohm resistance value. And when we do that, we should get about 3.88 is the total potential drop across the 2 ohm resistor. And this will be in volts. So that's the correct answer to part F. Let's see what we're doing in part G. Go all the way back up here. In part G, it says subtract the result of part F from the battery voltage, and that will help us find the voltage across the 3 ohm resistor. Okay, I guess we'll take their word for it for now. So we're going to subtract from the voltage of the battery. And so the voltage across the 3 ohm resistor, which we might symbolize like this, will be the voltage of the battery minus the voltage across the 2 ohm resistor. So the voltage supplied by the battery is 8 volts, and then we'll subtract the 3.88 volts that we just obtained. And when we do this, we get 4.12. fill in everything here. So the potential drop across the 3 ohm resistor will equal 4.12 volts. So this would be the correct answer to part G. Now, of course, that will warrant some explanation, which we will do so briefly here. Remember, the total battery voltage was 8 volts, so you can imagine a total of 8 volts coming across the circuit here. Now, at this point in the circuit, you still have a total potential of 8 volts. But then once the current flows through this resistance, there is a potential drop, as they call it. So we figured out that potential drop was 3.88 volts. So it starts at 8 at this point, it drops by 3.88. That means right here at this point in the circuit, we have 4.12 volts. Now, we have copied this picture from above, and we can see that the 4.12 volts will sort of split across a parallel combination. However, in parallel, the voltage will be the same on each resistor. So not only will the voltage across this resistance be the 4.12 volts, but the voltage across this resistance, the 3 ohm, is also 4.12. So perhaps that helps explain why the potential difference across this will also be 4.12 volts, and that was the answer to part G. Now in part H, we want the current in the 3 ohm resistor. So that's relatively easy. We come down here for our final picture. This is the original circuit, in fact, although we could have used the picture above. We have the resistance and the potential difference across that resistor marked 3 ohms. And again, we know that delta V equals I times R. If we divide both sides of the equation by R again, we can see again that the current will equal the potential difference divided by the resistance. So we just take the potential difference across that resistor that we obtained, divide it by the resistance value, and when we do that, we get a current that's flowing across the 3 ohm resistor equivalent to about 1.37 amps. So this would be the answer to the final part of this question.